Hello everyone and welcome to your lesson of physics. In this video I'm going to explain the recently added or the new added topic that is called momentum. This topic is added for the syllabus of 2023 onwards. So pretty much all the students who are now in O1, O2 and O3, they'll have to get done with this one topic, which is in the section of forces, once again by the name momentum. So there are some pointers that you need to cover in this one, and starting with the definition and formula of the momentum itself. Then the next thing would be defining impulse in terms of momentum, and the next thing would be the most important one, the law of conservation of momentum, and to apply this law or to apply this principle to solve some of the questions, to solve some of the problems in linear motion. And the last one is to define the force, to define the resultant force in terms of the momentum. Now the thing is, 80 to 90% of the questions from this topic are mathematical. And in order to solve those questions, you must be having a set of formula. There is a set of formula that you need to memorize as it is. Obviously, there has to be understanding of it behind those formula, but at the end of the day, there are certain formulas from this topic. Some of those formula they have mentioned directly that you need to memorize, so you would be able to solve 80% of the questions from this topic. Now I'm starting with a recap of some of the important pointers of this topic. I'm not going into the details. I'll be explaining in such a way that we head straight to the sample question and we should be able to solve the question straight away. The definition of the momentum is, some of the books call it the quantity of motion of a body. The quantity of motion of a body is called momentum. Mathematically, you define momentum as the product of mass and velocity. You see, in physics, if you multiply certain quantities, you always get a new quantity. Right? In many of the cases, it's just a way to understand momentum. So you can think about it. If you multiply mass and acceleration, you get another quantity that we call force. All right. Once again, just for the sake of understanding, let's do it this way. Or you can also say, if you have force into perpendicular distance, you get another quantity called moment of force. Or if you take force, product of force, and the distance covered parallel to the force, you get the work done. So similarly, if you take two quantities, mass and velocity, you multiply them, you get momentum, which is represented by P. So the symbol is P. If you forget the symbol, just write momentum as it is. Then the next thing is, whenever we define a quantity, then we are concerned with two things. What is the nature of quantity? Means, is it a scalar or vector? And second thing is, what is the unit of that quantity? So first one, momentum is a vector quantity, means it has direction as well. Your momentum is always in a certain direction. Second thing, the unit of momentum. Well, the unit of momentum can be obtained from the formula itself. All right, from the formula itself. Like this is a formula, and first thing that you have is mass. The standard unit of mass is kilograms times the standard unit of velocity, which is meter per second, or ms minus 1 meter per second. That will be the same thing. So the unit of momentum would be the combined units of these two, kilograms meter per second. Whenever you write your answer for momentum, you have to write kilogram meter per second with it, or you can also write Newton second. Because if we break down Newton second, then it'll be broken down to the same thing. All right, I'm not getting into the conversions right now, but Newton can be broken down as, sorry, this thing kg ms minus 2, and then you multiply by second, you get kg ms minus 1. Since momentum is a vector quantity, so it can be positive as well as negative because it's a vector quantity. The next thing is, generally, if the momentum of an object is towards the right side, we say the momentum is positive, and if the momentum of an object is towards the left side, we call the momentum is negative. It's just a convention. All right, it can be the other way. The next pointer. If two objects have equal mass and they're moving with equal speed but in opposite direction, the magnitude of momentum would be same, but the direction of momentum would be opposite. In that way, like I said, the momentum is a vector quantity, and if some object is moving forward, we'll just say momentum, moving towards the right side, we'll say momentum is positive. If it's moving on the left side, we'll say momentum is negative. Now this thing applies over here as well. When an object rebounds, let's say you throw a ball, you release a ball from the air, it hits the ground, it bounces back. When it was approaching the ground, its velocity was downward. When it rebounds, or as it rebounds, the direction of the velocity is now changed from downward to upward. In that case, the momentum is also changed from downward to upward, or the direction of momentum is also changed. The most important one is the law of conservation of momentum. The definition says, or the law itself says, total momentum of a system remains constant in the absence of external force. Or you can also define it, the momentum of an isolated system before collision equals to the momentum of the system after collision. That is also an acceptable definition. The thing is, this has to be memorized as it is. They ask you for 2 marks, and also there's a mathematical expression related to it. But what I suggest is you just keep it in your mind that the total momentum before collision equals the total momentum after collision, and from there you can derive the expression, or you can derive the formula by yourself. Because if you memorize the formula, it might be difficult for you to apply that formula in the question, because sometimes the objects are given in a different way. Sometimes the objects are joined together, sometimes the object behaves independently. So there you might be needing, or you might be needed to adjust the formula, which might be difficult for you. So for the law of conservation of momentum, total momentum before collision equals to the total momentum after collision in the absence of external force, or you can simply say in isolated system. When we use the word in isolated system, means a system where there's no external force. So the momentum remains conserved. Conserved, once again, the word conserved means something that doesn't change. The next important thing is impulse. Alright, so impulse, if you multiply the force, like I say, if you multiply force by distance, we get a quantity called work done. But if I multiply by the force by the time interval in which that force was exerted, or simply you can say force multiplied by the time, the quantity that we get after multiplying these two things is called impulse. And generally, like for the most part, whenever you are calculating the impulse, the time would be very small. The value of t would be very small. Because we are interested in calculating impulse whenever two objects are in contact for a very small interval of time. Example, when a ball hits a bat, the time of collision of the bat and the ball is fraction of a second. A football player kicks a football. The time of collision of the foot and the football is very small, fraction of a second. Similarly, in case of an accident, the time of collision or the time of impact is very small. In these kind of cases, we are interested in finding impulse. Now, once again, impulse, you have to memorize its formula and you have to memorize its unit. Its unit is just the same as the unit of momentum, and it can also, this one also can be written as Newton second, because the unit of force would be Newton, the unit of time would be second. The unit of impulse can be written as Newton second. Now, talking about the impulse. Impulse can also be defined as the change in momentum. That's another formula for impulse. The change in momentum. Alright, matter of fact, we can derive these formulas. All of these formulas can be derived from one another. But here's, you just keep it in your mind. You have two formulas for impulse. Number one, impulse equals to F into T or delta T. Number two, impulse equals change in momentum. For example, let's say the momentum of a system was 30 kilograms meter per second, and the momentum of the system changed to 50 kilograms meter per second. The question is, what is the impulse? Well, the change is from 30 to 50. It is 20. The change is 20 kilogram meter per second. So the impulse would be 20 kilogram meter per second, or you can write 20 Newton second, whatever you want. Generally, with impulse, we prefer Newton second, right? But it's not compulsory. The other thing, let's say the momentum of a system was initially 100 kilogram meter per second, and then the momentum was reduced to 0. Or it's not written 0. They say then the system comes to the rest, or then the object comes to the rest. What is the impulse? Well, previously the momentum was 100. Now as it comes to the rest, the momentum would be 0. What is the change? What is the difference between 100 and 0? It is 100. So the impulse would once again be 100 Newton second. So with the impulse, we don't write the negative sign. We just see the change. Even if it's from higher value to a lower value or lower value to a higher value, we just see whatever the change is. We subtract the higher value from the lower value. So the change in momentum, this thing can also be written as delta P. Alright, so in physics, this symbol delta represents two things. Either it might be representing change. So if it is written with delta P, that would mean the change in momentum. If it's written as delta V, that would mean the change in velocity. Delta S, the change in distance. Delta D, the change in displacement. So the word or the symbol delta represents change. Delta D would mean the change in velocity. And the other thing is delta also represents a very small quantity. Alright, so generally we use it in mathematics. Delta T approaches to 0. That means the time is very small, very small. Let's say 0.00001 second. But we don't use delta to represent a small quantity here in physics. In our syllabus, we mainly represent delta for change. So the change in momentum can also be written as P sub F, F in the subscript, minus P sub I, or PF minus PI. PF stands final momentum, minus pi stand for initial momentum. Final momentum minus initial momentum. So this is the second formula for impulse. Now the last thing is the force itself can be explained in terms of momentum. Matter of fact, when we completed the workbook of forces, I wrote down the definition of force as the rate of change of momentum. In A levels, you have to define force that way. The resultant force you have to define this way, the rate of change of momentum. So delta P represents the change in momentum divided by delta T represents the time during which the momentum changed. So force can also be written as delta P over delta T. This is another formula of force. You can keep it in mind. Just like you have F equals ma, you can also keep it in mind F equals to delta P over delta T. Now these are the tools. These are your tools, all the mathematical formulas, starting with this one. P equals to mv. The second one is the law of conservation of momentum. I don't write its mathematical expression. Matter of fact, we'll create the mathematical expression depending on the situation. The third formula is for the impulse in terms of force and time. Fourth formula is impulse as a change in momentum. Fifth one is just the same thing. And the last one is force in terms of momentum. So these are your tools which you will be using in order to solve pretty much all the questions from this topic. Pretty much all the questions. Like 95% of the questions would be solved using these pointers. Some of them would be definitions. That the important definition, once again, I've written over here. How do we define momentum? What is the law of conservation of momentum? How do we define impulse? These kind of things. Now we move on to sample questions. All right, so this is the first sample question that we have from the topic of momentum. So the thing is, as you read the information, you can highlight the important quantities. For example, figure 2.1 shows a dummy of mass 70 kilograms. Mass is given as 70 kilograms. You can write M over there. Used in a crash test to investigate the safety of a new car. Then you have the diagram as well. The car approaches a solid barrier at 20 meters per second. So this is the starting speed, the initial speed. It crashes into the barrier and stops suddenly. Finally, your car comes to a halt. Your car comes to a stop. Calculate the momentum of the dummy immediately before the crash. So before the crash, what is the velocity? This one, 20. So first of all, you write down the formula of momentum. P equals m times v. You get 1 mark for this one, for just writing down the formula. Then you insert the values. The mass was given 70 times 20, and that would be 1, 4, followed by 2 zeros. The unit is, like I said, you have to memorize the units, or you can generate the unit from here, kilogram meter per second. M/S you can write, or ms-1. Both would be acceptable. Determine the impulse that must be applied to the dummy to bring it to the rest. All right, so you go back to your toolbox. You see, for the impulse, we have written down 2 formulas. Impulse equals to force times time, this one, and impulse equals change in momentum, and that's it. So we see which one should be more appropriate over here. So you see, impulse, first of all, I'm writing down the formula for impulse. It'll be easy to apply this formula, or it'll be easy to calculate impulse by using this formula. What was your momentum at the start, before collision? It was 1400. What was the momentum after the collision? Well, the car eventually came to a halt it stopped, so the final momentum would be 0. So starting momentum is 1400 and the final momentum is 0. Now what is the change? What is the change, or what is the difference between the two values? And with the impulse you can write down the same unit, or you can write Newton second. Both would be acceptable. I'm writing Newton second because for impulse it is a better practice to write Newton second. All right, but you can write either of these two. In the crash test, the passenger compartment comes to a rest in 0.20 second. Calculate the deceleration of the passenger compartment. You need to calculate deceleration. There are two different ways. For deceleration, just calculate the acceleration first. And the formula of acceleration is v minus u divided by t. The final velocity was 0. Initial velocity was 20. Or was it? Yeah, initial velocity was 20. And the time is 0.20. Then you just hit it on the calculator and that'll be 100. 100 with the negative sign. This is your acceleration, 100 meters per second square. But you need to find the deceleration. Easiest way is find the acceleration. Now reverse the sign of the acceleration, you get deceleration. So if you reverse the sign of negative 100, it'll be 100. This is how you can find deceleration. Then we have the next thing. The seat belt and the airbag brings the dummy to a rest so it does not hit the windscreen. The dummy has in every deceleration of 80, which is smaller than the deceleration of the passenger compartment. So the dummy is experiencing a less change in velocity, or you can say the velocity of the dummy is not being changed quickly or not being decreased quickly. Or if we need to find the resultant force, F resultant equals mass times acceleration. Mass was 70, acceleration is given as 80. You hit it on the calculator and the answer for this one would be 5400 Newton. Like I said, deceleration of the passenger compartment is 100. Deceleration of the dummy is 80. The higher the deceleration, your change in velocity would be sharp, or your velocity would be decreased quickly. You'll feel a jerk. If your deceleration is slower or less, then your velocity would change slowly. You'll not feel a jerk. You'll not experience a large amount of force. If your acceleration is higher, you'll experience a large amount of force, and that force would produce a jerk on you. All right. So why this is of the benefit for the safety of the passenger? Which thing? Slower deceleration of the dummy and higher acceleration of the passenger compartment. So less acceleration correspond to the less force, because we know F equals to mass times the acceleration. If acceleration is less, the force exerted would also be less, and the passenger is less likely to be hurt. All right, then we move on to the next one. So we have this one question over here. Figure 2.1 shows a hammer being used to drive a nail into the piece of wood. The mass of the hammerhead is 0.15 kilogram. The mass of the hammerhead when it hits the nail, the speed of the hammerhead when it hits the nail is 8 meters per second. That's the initial speed. The time of contact is 0.0015. Like I said, would be a very small value of time. So the hammerhead stops after hitting the nail. So the final velocity of the hammerhead is 0. indirectly given. Calculate the change in momentum of the hammerhead. So the change in momentum can be written as delta P. Delta once again represents the change in momentum. Now once again, if you scroll back to the toolbox or to the formula list, you'll see the change in momentum is final momentum minus initial momentum. Final momentum minus initial momentum. Final momentum can be represented as P sub F. Initial momentum would be P sub I. Now the question is, how do we find the final momentum? Well, the formula of momentum is mass times velocity. If you need to find mass times velocity, if you need to find final momentum, multiply mass by the final velocity. If you need to find initial momentum, multiply the mass by the initial velocity. So the mass is 0.15 times the final velocity was 0. This is your final momentum minus mass 0.15 times the initial velocity was 8. Then you hit it on the calculator, minus 1.2. The change in momentum, kilogram meter per second. But like I said, when you're finding the change, you don't need to give your answer with the negative sign, right? Whatever the change is, for example, from 20 to 80, what's the change? 60. Or even from 80 to 20, what's the change? What's the difference? 60. So you can write 1.2 kilogram meter per second. If you write your answer with the negative sign, it is acceptable. They'll not deduct your marks, but it's not a good practice, right? So you have to be clear with these two things. The next thing is impulse. Once again, you go back to the toolbox, you realize that there are two formulas for impulse. One of them is F into T, and the other one was impulse equals change in momentum. And you'll notice that if we use this formula, impulse equals change in momentum, we have already calculated the change in momentum in the previous part. So we should be using this formula, impulse. It's not important. Some of you students will read it as important. So I better write impulse. Impulse equals delta P, which is a change in momentum, and the change in momentum is 1.2. So you can write 1.2 kilograms meter per second or Newton second. Either of the unit can be written. A better practice is with impulse write Newton second. Average force. All right. Now for the average force, we have a formula that average or resultant force equals the change in momentum divided by the time in which the momentum is changed. Then you write down the two values. The change in momentum we already calculated, 1.2. In how much time the momentum was changed? T was given as 0.0015. You write 0.0015 over here. And then you just hit it on the calculator. It'll be 800 Newton. So this is how you can find average force, and this is how you can find impulse. This is how you can find change in momentum. All right, the last question from here would be how to use the law of conservation of momentum, and that question is one of the most important one of the trickier ones, and it is generally of 3 to 4 marks. So just let me raise off the stuff from here. So you have two toys, a moving engine, a toy moving engine, and a toy stationary truck. The truck is at rest, means its speed is 0. It's not moving. So if its speed is 0, the speed of the truck is 0, then automatically the momentum of the truck would also be 0. Momentum equals 0. Whereas the engine is moving, so, and it has mass as well, so it would be having some momentum. All right, let's check out the data. Before the collision, the toy engine is traveling at a speed of 0.32 meter per second. So the speed of this vehicle, toy vehicle, is 0.32 meter per second. And the mass of the engine is 0.50 kilograms. Calculate the momentum of the toy engine before the collision. Well, if you have the mass, if you have the speed, what else do you need to calculate momentum? You just write down the formula first. P equals to m times v. The mass was given as 0.50 times 0.32. You multiply anything by 0.5, it is reduced to half. So that'll be 0.16 kgms minus 1 or kgm/s. Both units are acceptable. Now, this is the interesting part where you have to apply the law of conservation of momentum. I mean, they have mentioned explicitly as well. Sometimes they don't mention it. You have to just find it out by yourself, that you'll need to apply the law of conservation of momentum. The law says, if you remember the law from the toolbox, the law says the total momentum before collision equals the total momentum after collision in an isolated system. All right, and all the system that you get will be isolated systems. So total momentum before collision equals the total momentum after collision. Well, let's check out what is the total momentum before collision. So you'll have to add the momentum of the moving engine and the momentum of the truck before they collided, and then you get the total momentum before collision. Well, the total momentum of the engine was 0.16, and the momentum of the truck, since it was stationary, it was 0. So you add these two, what do you get? You get 0.16. So this is your total momentum before collision, 0.16. 0.16. And that should be equal to the total momentum after collision. So the total momentum after collision, whatever the expression for that is, should be equal to 0.16. But let's find out what should be the expression or the formula or the mathematical equation for the total momentum after collision. Well, the situation is your engine combines with the stationary truck. They behave as a single unit once they collide. So let's say this is your all right, it's just a block diagram. This is your engine. After collision, this engine combined with the stationary truck. Now they behave as a single unit. Now you can think about it, this whole thing, the whole object is a single toy. What is the mass of, in order to find the momentum of this whole thing, you need to find the total mass of this thing. Well, you can find the total mass by adding the individual masses. Mass of the engine was 0.5, mass of the truck is 0.3. So 0.5 mass this one, 0.3 mass for this one. So the momentum equals to mass into the velocity. The mass of the combined object is 0.8 times the velocity is v, because we don't know the velocity. Matter of fact, velocity is the thing that we need to find. And what velocity is that? It is the combined velocity by which this object would be moving forward. Alright, so this is the velocity that you need to calculate. And this is the final momentum. This is the expression for the final momentum. Now this, according to the principle of conservation of momentum, should be equal to initial momentum. So we can write momentum after collision would be 0.8 times the capital V. Now you can obtain the value of capital V from here. This thing 0.8 would be shifted on the other side. It'll go in the denominator, divided by 0.8, and that leaves you with the value of v, capital V, the speed. What speed? The speed of the whole unit by which it's moving forward. And once you hit it on the calculator, your answer will be 0.2, and the unit of speed, everyone, it is meter per second. So this is how you can apply the principle of conservation of momentum to find an unknown quantity. So not only, sometimes they'll give you the value of speed here and they'll ask you for one of the masses. So you'll have to just write down the expression for initial momentum and expression for the final momentum. Either initial or final, one of the values would be obtained mathematically. Like in this one, we obtained the momentum before collision as a numeric value. The other value is not a numeric value, it's an expression, and we can find the unknown quantity from there. So these are the different kind of questions that you can get from this topic. Finding impulse, finding momentum, finding the average force, finding the change in momentum, finding the deceleration, and applying the law of conservation of momentum. So that's the end of the video. Don't forget to like and subscribe. Thank you.